All right, in this introductory screencast, I'm just going to kind of go over the difference between a population and a sample. And this is really important to understand when we're talking about statistics and data analysis. So let's just start with an example that's going to kind of demonstrate this concept. Perhaps we wanted to calculate or determine the average height of American males. Now, the population that I have represented by this green circle is every individual male American in the population. So this will represent all values of the variable, which is generally unknown. It's going to be very difficult to survey or obtain experimentally the heights of all American males. I mean, you'd have to go through several 100 million American males to determine the actual population, the actual average height of the population. Instead, what we typically do is we take a sample. So we take a small sample of measurements, also known as observations, and this is going to be a sample. So maybe we have, several dozen samples, and there's various ways to determine how many samples to take depending upon the spread in the data. Many random variables are normally distributed, so it might look like this, and we have our actual population mean, which again here would be the average height of American males, but that corresponds to the population. When we take our sample, we're assuming that we're taking enough samples that we kind of, these are all samples here, and we're getting, this would be height of males, and we're getting a representative sample of that population. So we have a population. Typically, it's very difficult to obtain measurements for the entire population, so we take a small sample. The sample average would be a good estimator for the population average. The distribution has two measures. It has a measure of central tendency. So this is central tendency. In a lot of cases, we use the average or the mean of that distribution or the sample. But it also has spread. So how far this distribution is, whether it's wide like this, or maybe we have a much narrow distribution. So that's related to the variance or how variable the data is. So likewise, the sample variance would be a good estimator for the population variance. So we use the sample statistics, the sample average, and the sample variance, which you'll learn about in a subsequent screencast, in order to make inferences on the population. And hopefully, the sample average, sample variance is a good estimate or a good indicator of the population average and the population variance. So how do we characterize samples and populations? We can look at the various statistics here, count, mean, and variance. The population we denote by capital N. So that's the actual total number of individuals in the population here, the items in the population, capital N. Our sample, we take a much, much smaller sample of lowercase n. So that's kind of the terminology here. There arises an issue of how big of a sample to take, and we'll talk about that later on in the course. Do you need a really big sample, or can you get away with a much smaller sample? The population mean is given by this Greek letter mu. So that's the actual mean of the population. And again, theoretically, you couldn't know this without calculating the average of all of the items in the population. So in our example for male American height, then we would have to get the height of every male American and then take the average, which we can't do. So instead, we calculate X bar. So this is the notation for calculating the average of a sample. The variance or the spread in the data, that's sigma. This is Greek letter sigma. So sigma squared is known as the population variance. And we can estimate that using our sample variance, and that's S squared. We can take the square root of the variance and we just get sigma. Sigma is known as the population standard deviation. Likewise, we can take the square root of the sample variance and we end up with just S, and S is the sample standard deviation. So I just want to kind of show you this. If we have a normally distributed variable, it doesn't have to be normally distributed, by the way. So if we had a population mean, this is going to be our population, then each of our items, so if I took items here in dots, I'm just taking measurements of the population, we can represent each observation from the population as the following. X, which is our random variable, so that'd be male, American male height. It would represent a measured quantity, and it's going to be equal to the population mean, mu, plus some sort of random disturbance or noise, which we denote by epsilon here. So if I just took 4 observations from our population, 1, 2, 3, and 4, each of those observations is equal to the mean, denoted by this blue dotted line, plus some sort of individual error for that particular measurement. All right, so this might be epsilon 1, epsilon 2, and then we have an error from the mean of the third, so that's epsilon 3. You'll also see these referred to as residuals, so they're error values, but that's how we can basically relate the mean and error to any individual measurement in the population. Actual measurements can have variability. If you were to give 3 different people a tape measure and have them measure my height, for example, you might get slight variation. So measurements can have variability. Manufactured items can have variability. Sales will vary from day to day, but each of those can kind of relate to this equation up here where any individual observation is kind of a long-term mean of the population plus some sort of individual error from that mean. I just wanted to finish this screencast by explaining a little bit about why we might want to use samples. Well, just as a simple example, the number of M&Ms in a bag might vary from bag to bag. There's variation in the number of traffic accidents in a day, the reaction time of a driver. So drivers have different reaction times. Maybe you're looking at sales, so the items sold in a day or the sales in a day. Stock prices kind of go up and down. They fluctuate over time. Election polling is a sample of the population. You obviously can't survey every individual of the population, so we can do polls. And then finally, the number of defective light bulbs in a pack of 4. So you go to your hardware store, the number of defective light bulbs that you purchase in a pack of 4, it might be small, but it's going to vary from pack to pack. So this screencast kind of gives you a summary of the difference between a sample and a population. Thanks for watching.